Good afternoon, everyone. I am Gilberto Thomas. I am a long-term collaborator with Professor James Glazer. I'm from Brazil, and I am a regular instructor in this workshop. And I have been working with CompuCell3D since its foundation, creation, if you want so, more than 20 years ago in Notre Dame. Okay. Today I'm going to present you some cell properties and behaviors which that are determinants for the cell shapes. Okay. Let's see. Um, the motivation for this presentation and for the tools that I am going to present you is the variety of cells we have in an organism. Okay, and this is the motivation, and this motivation will serve as the base for to execute some exercise which will present you with more detail some basic plugins of CompuCell3D and how those plugins can be used to control the cell shapes. Okay, okay, talk about the cell diversity. See, we can have in nature lots of cell shapes like erythrocytes, epithelial cells, muscle cells, and nerve cells, reproduction cells, and each of one has its own structures and characteristics. In particular, epithelial cells can be modeled with more uh, through with easy use of some plugins in this CompuCell3D, for example, to form epitheliums like squamous, cuboidal, columnar, and so on. Okay? Let's start by building a basic simulation. You know, this we are being repetitive in these 2 first days because you guys are knowing this code. So let's start from the beginning, create a very basic simulation. Okay? We start with a TwoEdit, and from the TwoEdit we will open the wizard to build a new simulation. But you can download any of this exercise you are going to build here online in the presentation from the students materials demo code folder in the website. Let me remind you that for all this exercise, we will have a corresponding exercise file in that folder. Okay? Okay, let's do it. Okay, then this is the first exercise. Here is the step-by-step uh, uh, procedure that you have to go. You open TwoEdit, you call, start a new project, give it a name, for example, module 2.2 cell shape, and select Python XML. Go to the step 3, adjust the lattice dimensions to 100 each on X and Y, and make sure you choose the rectangular slab for initial configuration, initial cell configuration. Now you go to the next window in the widget, the wizard, and create a single cell named, for example, test cell. Add it to incorporate in the table. Go to the next table, next step in the wizard, ignore chemical fields, and include the plugins volume flex, surface flex, length constraint, and center of mass and go to the next one to finish simulation. Let's see one by one of these steps. Here is what I just showed. To edit, open a new project. Okay? In this project, it will open. You give it a name here. This is the simulation directory you have to choose. This is up to you. Hit next. Adjust the let's dimensions to 100 each. Only choose a rectangular slab here and hit next. I'm going a little bit fast because although we're going step by step, you already know this first step here. Type in the name of the cell type you want, test cell, add it to the table here, clicking add. The name will appear in the table. Hit next. No, ignore the chemical fields. We don't have any yet so far. And use, load the plugins, the cell properties and behavior. Contact energy, volume flex, surface flex, length constraint, and center of mass. Hit next and finish. Now let's go over the files, okay, just to be if everything is okay. When you after the wizard is closed, you click in the name of the project in the to edit editor in the CC3D simulation tab, and this will open the files in 3 tabs in the right window. Go to the first one, which is the .py Python, and this Python is the main Python file. In this file, we use this file to register the steppables that you are going to use, and any other engine from CompuCell3D that you want to include in your simulation. So far, we just use this first, the single one, the default one, which is cell-shaded steppables. The second file is the XML. The XML is where your simulation is configured. You have some regions here, some tags. The first one is about metadata to choose if you have one or more processor using to run the simulation. The output frequency means which frequency the screen will be updated. Then you have the tag pods where you define the grid dimensions, number of steps the simulation, the temperature, the neighborhoods for the spleen flips, the site flips change, the first neighborhood. The cell types here. We have the medium one, which is default in the CompuCell. It's always there, and the test cell that we have created in the wizard. Then we have the 3 plugins we have loaded: volume, surface, and center of mass. And the next one is the next one, which is not shown there, is the length plugin. The third file is the steppable files. The steppable file is where you write anything you want that your simulation calculates or shown in your screen. Those are user-defined instructions, or in these steppable functions are included some steppers that you might include in the wizard. We are going to see this later today with some others steppables like its growth and division. Okay? For now, we have only this structure here. The steppable has uh, five functions where you may edit or not if you want, if you need to. Initialize some extra parameters for your simulation. Then the start function will put instructions that run only once at the beginning of the simulation. The step function, the instructions that run each Monte Carlo step, each time step of the simulation. When the simulation ends, the CompuCell calls this finish function to wrap up the simulation. And if the simulation is stopped before the finish, before the regular end, then it calls the one-stop function where you write here something that you want to, to print in the screen if you have to stop the simulation sooner than the regular one. Okay? Okay, now we are going to run the simulation. Everybody can do that now. You go to the CompuCell cell name, project name, right-click, and open a player. Of course, you can also alternatively open the player clicking on the logo CC3D on the tab up in the wizard, up in the editor. Okay? So when you open the player, you already know that, but just remember you have 4 blue buttons, and these blue buttons can control the simulation, the playing of the simulation. You have the play button, the step-by-step button, the pause simulation, and the stops that ended the simulation. Okay? See here in the red frame, you can see where this simulation is in the student, the name of the file it has the simulation in the student materials demo course. Okay? So if you run that simulation, you're going to see this. Those are 3 time steps of the simulation where you start with a bunch of cells because you have chosen only one type of cells in a grid 100 for 100. And as soon as the simulation runs, the cells start to change its shapes and end up by round the whole aggregate. Okay? Can everybody see that in your simulation there? I cannot really sure. Okay, my chat window was closed. Okay, let's move on. Next, we have to go to understand the effect of each of the plugins we have loaded. We have to go to a single cell simulation. Okay? Now, then we're going to build a single cell simulation. It's basically the same simulation you have. You can edit the one you have, or you can start from the scratch and build a new one. The main difference here between this new one and the older one is that we are going to change the the uniform initializer down in the XML file to redimension the box mean and box mine for the cells to be created. And then we are adjusting the width of the cell. Instead of seven voxels for each side of the cell, we are going to change it to 20. Okay? So let's go there. So go to the XML file you have, okay? And go to the steppable uniform initializer. So this is what you have now in the previous simulation, which means box mean is the left bottom corner of the square. Box max are the coordinates for the upper right corner of the green square in your window, simulation window. 7 is the size of the cell which you have now. And we are going to change that to these values. We're going to change x and y from 20 to 40, and in box mean, and in box max, x and y from 80 to 60. That means we are shrinking the grid size, the simulation size for this size here. And we have to change the width of the cell from 7 to 20 to fill up all that box mean, box max with only one cell. Okay? Because see it from 20 for 40 to 60, you have 20 voxels, and that's exactly the size of the cells we want. Okay? So save the simulation and run. What we're going to see is that the cell starts with the big square 20 by 20 and shrinks. Everybody can see that? In your simulation? Good. So the question is that if you don't pay too much attention, you barely can see the shrinkage of the cell. It's better to stop the simulation, go step by step, using the bottom step to see the cell shrinking very quickly to a small and kind of diffuse blob wandering around the screen. Okay? Why does that happen? Because now we have to consider that all the plugins we have loaded in the wizard are functional. I mean, the volume plugins, the surface plugin, and the length plugins. All of them are working at the same time. That's not a good idea to see how each one works. Okay? Then we are going to change that. We are going to turn off some of the plugins and work one by one to see the effect of each one. You see? Let's go there. So let's have a look of the plugins you have. We have these 4 plugins loaded at the beginning: contact, volume, surface, and length. Okay? This is where we loaded. They all are constraints that enforce these properties: volume, surface, and plugin. What does I want to mean with that? I think volume plugin says that you choose at the beginning that, for example, the 20 by 20 cells, and this volume will use that value at the beginning But when you load it, you have to define what is the initial value for the real cell. Remember that in the uniform initializer, you are only defining the initial size of your grid. Okay, but the size of the cell is regulated by what values you're using in this kind of plugin here. And this plugin is working this way. Is in this equation here. H property, it's the energy, is a lambda factor with a constant factor, and a function which is a square of a difference of the initial value, I mean the target value, which is the value that we want that the cell has, and the property value is the value which the cell has during the simulation. Because of the spin flips, the side flips, the cell is always changing his volume, his property, trying to, and this function here tries to prevents that the property value departs too much from the target value. So all the site copies that brings the cell close to the targets are favored. All the cell site copies that deviates from these values are unfavored. Okay, so the target volume is the value of the characteristic of the cell that you define at the beginning of the simulation. How to enforce that with lambda property. Okay, let's see how it works. Let's see. This is the function volume, surface, and length. The shape of this function is like is a parabola. Okay, so it's, if you remember a little bit of physics, it reminds you elastic energy elastic of a spring. If you detach the spring from some, if you detach this, how do you say? I forgot the word. Fast the spring from the part from the regular size of the normal size of the spring, the energy accumulated in the spring grows with the square of the displacement, not with directly with the displacement. So the energy goes to the square of the change. And that is valid for all the plugins. Always have the same behavior. And here is the property value for each one of the plugins and the target volumes of each one. Lambda volumes are parameters that tells you how much the cells will resist to changes. It can be very high or very low. That's up to your simulation. Let's go on. So now let's go a simulation, build a simulation only with a volume constant. Again, you can use the same simulation you have, but you can start from scratch. Yeah? Here is the simulation. Go back to the simulation you have, and then you are going to put 0 to both lambdas, surface, and length. What does that mean? Means that we are turning off the plugins. Remember, lambda is the factor in front of the energy term. If it is 0, there is no energy. So it doesn't contribute to your simulation. Okay? So how do you do that? Go to the XML file here. Go to the line where you have the plugin. surface and put 0 where you had 2. The same, see, that is the effect. You are putting 0 in this term here. The same happens, same you should do for the length constraint plugin. Go to the line where you have the lambda length, put 0 instead of 2, and again, you are canceling the influence of the energy term. Oh, save it again, step by step, no, I told you, and play the simulation. Now you see that the cells still shrinks and still wanders in the grid, in the LEDs, in the space. However, the shape of the cell is more smooth. If you compare with the old one, with the previous ones when everything was working, we have this final configuration for the cell, and now you have something more rounded for the simulation. Again, if you want to download the code, the code has this name, 2.2.2. Okay. Okay, this is what we didn't play with the volume yet. Let's go there. Now, why does the volume reduce? Well, if you look at the previous slide, the volume starts with a square which has 400 sides because the size is 20, and it ends with a small blob. The reason is because by default, CompuCell loads the energy plugin, the volume plugin, with a target volume valued 50. So as I said before, target volume, the plugin volume, enforces that the cell always has the target volume. So despite you start the cell with 400 voxels or pixels, whatever, at the end, the target will be 50. And the oscillations of the cell volume will occur around the volume of 50, not around the 400 you have at the beginning. Okay, then you change that. Now, looks like 4 cells. Maybe you didn't change the width of the cell in your simulation. You had to change it from 7 to 20 at the beginning in the XML file. Okay, so how to fix this? This is what we're going to do. Go to the line in the volume plugin where you have the target volume and change it from 50 to 400 and play the simulation again. What you're going to have is that your cell will not shrink anymore. It will be round, but now rounded with 400 pixels as target volume. Okay, so change this quantity, adjust the cells for the size you want during your simulation. Everybody can see that in your simulation? Okay, thank you. Now, you can play a little bit with some some target values. For example, change it on that line for from 400 to 30 or to 1,000. What's going on? Can anyone see what's going on with the fan? Why he has 4 cells, please? Okay, so if you put 30, you get a very tiny cell. If you put the target fixed to 1,000, the cell will grow from 400 to 1,000 during the very first steps of the running. You can try another thing. Put VT to 0, the target volume to 0. What is going to see? That the cells will disappear. Of course, because if you put target to 0, the cell will shrink until disappear. Actually, this is a way to kill a cell in CC3D simulations. If you are running a simulation of a bunch of cells and for some reason a cell must die, then you can put his target volume to 0 and the cell will disappear of your simulation. Okay? Another thing you can see, if you try some target volumes below V target, below 30, for these values, the cell also tends to disappear. We will talk to this later, okay? Now let's go move on. I hope everyone could see these effects of changing the target values on the simulations. Now, in the same plugin, in the same exercise, we are going to change the lambda volume. We are going to keep the volume target, the target volume equals to 100. You are going to play with the lambda volume. Remember, the lambda volume is the parameter which tells you how resisting the cell is in face of changes. Okay? So you have here the simulation as is now, but if you go now to change that value to 100, what's going to happen? Let's see. Change it from 2 to 100 in the simulation, in the file, XML file, and put the simulation to run. What you're going to see is something like that. The cells start as usual as a square, growth, because his target is 1,000, but a growth in a very rough shape, and he barely moves. I mean, the boundary of the cells barely moves. Why is that? Well, let's see. Because, of course, what we have done is to increase the lambda volume. And since, once that the cell reaches the target value, they decrease the rate of growth because any change in the energy implies in a big penalty of the function, the energy function y. Let's see why here, because of this. See what we are doing. The blue one is the previous lambda equals to 2, for example. When you increase lambda volume to 100, what we are doing is to close the parabola. So when you close that, any small variation around V target gives you a big change in energy, which penalize the energy minimization, which is the base of the model, the engine, the Potts model. So the cell stops to exchange, to flips with the medium, with the environment, and they almost freeze. Okay? So this is what happens when we increase lambda. You close the parabola, making any energy change very high. Remember, energy change goes with the square. If the square is multiplied by a big number, you have a big result. Well, let's go on. So if you want to, there's another thing, interesting thing. If you want to immobilize a cell for a while during the simulation, you can, for a certain amount of time, to increase lambda volume. Then the cells will keep quiet for a while. But why is 100 is a critical value? We have to understand, we understand that graphically in the function, but still we have some changes in the cell boundaries, okay? And that happens because there is a kind of competition between the energy term, the energy variation, and the temperature, the membrane fluctuation amplitude, which is called temperature in the XML file. That temperature says you how much the membrane should fluctuate. The bigger the temperature, the more the fluctuations are. Okay? But in this simulation, we only change lambda, not the t. So what we have done is that. See? Here is a graph showing is the probability of acceptance of the site flips. Remember, the site flips is made with this delta t. If delta t decrease, then the change is accepted with probabilities close to 1. Is this region 1 here? For any decrease in the energy, the site flip will be accepted. However, if the energy increases when the site flips is proposed, still you have some probability to accept it. It's a stochastic model, remember? So the probability is given by this spectrum. Is an exponential with the negative of delta H over the temperature. And this is give you this function here, exponential. See, the bigger the increase of energy, the less is accepted the site flip. Okay? And now we just mess with this lambda volume. When you mess with lambda volume, you are messing with delta H. But the temperature remains constant. So let's see what happens when you change the influence of the temperature in the simulation. Okay? So again, use the simulation you have to see that you have at the beginning by default CompuCell loads the POTS tag with temperature equals to 10. we were going to change this value here. Go to XML file and change to 100. Keeping, again, lambda volume equals to 100. So we have changed both lambda volume and temperature by a factor of 10. No, here was a factor of 50 and here a factor of 10. What do you expect? Would be the same if you have, for example, 10 and 10, because you have changed equally both parameters, the same order of magnitude, 10 to 10, 10, 10 to 100, 10 to 100. Let's run the simulation and watch what happens. Is the right figure here is what you should see. The left one is the previous one with temperature 10, lambda volume 100. Temperature 100, lambda volume 100. See? Now, the cell is not frozen anymore, but the surface, I mean, the boundaries of the cell are very hot. Why does that happen? Let's see. See, we have two competitive terms for now. Remember, we put to zero the surface and the length, but we still have the contact besides the volume term. So both terms compete because the total energy is the sum of those two terms of energy. The contact energy gives you the interaction between the cell and the medium, the black background. Okay? The volume, the volume gives you what we have seen, the size of the cell. When we change the temperature, we are messing only with the volume energy, volume constraint. Because when by increasing the lambda volume, you compensate the increase of temperature. Remember, we have here, we have a ratio between delta H and T. Since you are increasing only delta volume, delta A comes from volume term, the delta H comes from volume constant, the contact energy remains the same. So the competition here between those terms make the relative contribution of the contact energy decrease. So the border of the cells move more, fluctuate more, because the contact has less influence when the temperature and the lambda volumes are high. Okay? So to keep a smooth boundary is not a priority for the simulation. The priority is to keep the size big. Let's see this if now we change the temperature from 100 to 1, what happens? See? You still have movement. I mean, movement, no, the cell grows, change its shape, but the cell was frozen when T equals 1, because when you divide this, when you use this very small value for the temperature, what's going to happen here is the following. See, remember the function e to the minus h to delta t. If delta t is big, the ratio delta H of t decrease. So the probability of changing of the accept flips increase. If t is 1, delta H of 1 increases, and the probability decrease goes to this part of the graph here. So the cell freezes, doesn't move. Okay? Is that clear to everyone? Let's see. Yes, well, the bigger the t, the more flips are accepted. Because if you decrease this ratio, and since it is a negative exponential, the fraction increase. Okay? Okay, let's move on. How much time do I have, Ed?
Keep going, you have plenty of time.
Oh, good. Now, let's go to the next one. Let's include the surface constraint into play. Again, the surface constant has the same shape. It's lambda times square of displaced in surface, expressed in number of sides. Actually, see, I should remember that we are doing this in 2D. So volume for us is surface area. Okay? Just to, and the length boundary is perimeter, not surface. Okay, just to keep in mind that. So the surface is here. Is measuring units of size. Is that what you just said? Surface now is perimeter because you are counting the number of the sides of the cell has. For example, here in the left, I don't know if I can use a laser pointer here. Okay, here. You have a single cell with only one side. It has 4 sides. This is a perimeter. And the volume is the surface, 1. Here, the volume is 4 sides. I have 4 sides. So the surface, you have to count the interfaces between the cell and the grid sites. 1, 2, 3, 4, and so on. And so on, a bigger one here. As the surface is 20 sides, but the volume is 21 sides here. So a good, let me get rid of this. How do I go there? Okay. Next, okay. So in a good approximation, we can write this equation between volume and surface. Volume as the surface is 4 times the square root of the volume. I mean, think here, for example, the volume is a square of side 4. So the volume of this square is 4. The square root of 4 is 2 times 4. You have 8 sides. Okay? Here you have a little bit distortion from this equation, but it's a good approximation for a start. Okay. You can, again, take the same simulation, but you can load a new one from or start a new one from within the wizard, or load this from the student's demo, the demo codes. If you are use the same one, reset the parameters now, the simulation you have, going back to these values. Okay, you go to the temperature, the equals to 10, lambda volume equals to 10, VT target volume is 1000, and you are going to turn off the contact energy here to see how volume and surface interact, both plugins interact, play together. Yeah? So putting J medium test cell equals to 0, we are zeroing the contact energy between the cell and the medium. And let's use this relationship here to give it to the cell a target value of 126, which is this 4 times the square root of 1000. The contact energy in the XML you change in the plugin contact. Sorry, I forgot to say that. You have the matrix with the interaction energies between medium, cell. Put to 0 in, set to 0 the J medium test, cell. Okay. So, and now we are redefining the lambda surface from 0 to 10. Remember, previously we were using lambda surface 10 to turn the surface plugin off. Now we are turning it on back. So put it 10 and target value as 126. Run the simulation now. Let's see what happens. This is what you should see. Remember, we check if you have all these parameters in your simulation. T equals 10, lambda volume 10, V target 10, lambda surface 10, surface target 126, J medium cell 0. And now when you run the simulation, basically nothing happens. The cell barely moves. I mean, the square shape is kept. Why? Because the simulation is trying to satisfy both plugins. Okay? It's not paying attention to, there is no interference of the contact plugin, which would help with the curvature, take into account the curvature of the cell with the medium to change the energy, but we have put it to 0 to avoid that. So it is trying to satisfy the VT 100 with the ST 126. Then you have the square. Everybody got that? Good. Now, let's explore different values of S. Let's change S. You can play now for a while. Okay. This is what you should have. Change in the ST values. First, start with smaller values. and then go to very big values. This is what you should see in your different simulations. I will give you 2-3 minutes to try it, to see if you get those images. So let's analyze. So if you, sorry, if you decrease the value of S target, the cells doesn't shrink because the target volume is kept the volume constant in 1,000. Okay, if you increase the target, then this is the default one where we start from. When we increase it, the target, the cell is allowed to change its shape to achieve this value for the surface target, 105, for example. And if you continue growth, increase this target, the cells will try to achieve this number. And the way it finds to achieve this number is start to fragmentate itself until this extremely high value, 2,000 here, where the cell is stored apart. There is nothing left in that. Okay? So this is the effect of that. Moving on. Finally, let's see sorry, the effect of the length constant. Again, we have the same kind of expression for the energy term, a lambda factor time square of the changing in the length. We have a target length and the actual length, let's say that during the simulation. And let's reset again the simulation. Does the major axis of the cell change as the shell should? No, it's not fixed. It should change. The cell, there is no constraint on the axis right now. Okay, for the next one, let's put 10, temperature 10, lambda volume 10, V target 10, and go back to lambda surface 6 to 0. So let's turn it off again, lambda surface. And let's come back with the contact energy between medium and test cell to 10. Huh? So this is, let's use this expression now. Again, the size of the complement of the cell is square root of the volume of the cell. In this approximation here, we are supposed that, for example, the cell is a circle. No, the cell is a square, and the size of the square is a square root of the volume of the A. Okay, so this 32 is the square root of 1,000, approximately square root of 1,000. So this is the cell length. Let's put these values in the length constant plugin in the XML file here. That's lambda length equals to 5 and target length equals to 32, the calculated value through this formula here. So remember, just to reinforcing is the diameter of a 2 square, let's say, circular shape. Okay? Now let's play with the target length of the cell. For L equals to 32, you run the simulation, you see this thing. Since we are taking this length from the original cell size, which is a circular one with 1,000 voxels of volume, you have a rounded shape. Now, let's change this value for these three quantities, 40, 60, and 8. Try it by yourselves there. Yes, thanks, James. You did the code, put it to run with those different values and see if you get those shapes. Everybody could see that? Length equals 200. Of course, the cell is bigger than the grid. So it sticks to the border of the grid, and it splits into parts. Yeah, every time in that simulation, every time if you don't at the beginning put some restrictions, if the cells touch the border of the grid, it sticks to it. So for the simple simulations, we take care that doesn't happen, and we don't have to worry about these simulations problems. They stick to the boundaries. Okay. So I think we can go now for smaller than 32. What happens? Let's see. Change it for lambda 5 to, this is the original one? Oh, not original. Now you are going to L to 10. And here we are changing the length constraint to, oh, sorry, I put a wrong slide. Oh, no, we are changing the length constraint now with lower values of the cell. Well, for lower values of the cell, I didn't write here. Probably you will not have much effect in the shape of the cell, because the volume will keep the cell big, you know? So the volume constant will prevail against the length constraint plugin, the energy term, okay? But if you change the surface, the length constraint, lambda, if you increase it, you have, again, this kind of fragmentation, the start fragmentation of the cell, because the flips start to be not accepted because of remember, when you increase lambda, the constraint, the parabol close. When the parabol close, you increase the penalty for changing flips, and the flips are mostly rejected. So the cell freezes and keep this this roughly shape in the cell. So this is what I said. I forgot to point. This is what you mean. So this is a warning. Usually, if you set an unreleased constraint, it can freeze your cell and your simulation doesn't work. So here I finished this presentations for today. I think if we could show you some influence of this, how those plugins, surface, volume, and length works together and separately in the cells. And this is so are good tools that CompuCell3D brings to you to help you to model a very realistic simulations from the beginning and to be able to answer that bunch of questions that Professor Glaze made this morning when you have to start to thinking in the simulation and think what answers do you want to solve. But to see what answers you want to, what questions you want to answer, you need to see if the code is able to answer. And here you see that at least with the shape of the cells, you can do a lot, okay? So thank you for your attention. I just finished early today. I think not coded on the screen saves time.
Sorry, Gilberto, did you launch the poll?
I will do. I'm trying to do that. Is trying to figure out where is the poll because I have to.
I've got it.
Can you launch it for me?
Is the poll that's up the old one?
Ah, good. Thank you.
Please fill out the poll. There's a question about if you stretch a cell too much, why does it get thinner? And the answer is that that's called the capillary instability. And you actually see it with water drops. If you try to stretch a water drop too much, it'll split into two round drops because the surface of a long elongated ellipse is longer for the same area than for two circles. There's another question. If you put the temperature close to zero, what will happen? And the answer is if you could put the temperature very close to zero, then energetically favorable copies will happen, but energetically unfavorable copies won't happen, and the simulation will freeze rapidly.
The same what happens in that surface when we put t equals to 0 there. I showed that graph with probability of acceptance when the t equals to 1, the function decrease very quickly to 0.
There was also a question, could I ensure which constraints are stronger by playing with the lambdas? Absolutely. You need to adjust the lambdas so that all of the constraints are doing something. If you make one constraint very large compared to the others, effectively the other constraints don't do anything. And that's something you may have run into if you've ever worked with loss functions in machine learning. Tuning the loss functions when you're doing multi-constraint optimization can be pretty tricky because you need all of the different features to play a role at the same time. And so you need to tune the strength of the different components of the loss function. So actually, in the old days, these kinds of optimization weren't so familiar. These days, when people are doing data science and machine learning, the kinds of constraint-based optimization we're doing here actually are pretty familiar. Even the stochastic optimization is pretty familiar. If your cell is still looking like a square rather than changing shape, there are a couple of possibilities. One is that the target surface is too small compared to the target volume. Another one is that you're using a nearest neighbor contact energy. Another one is that the fluctuation amplitude or temperature is too low. So that's one where maybe it would be good for you to go into a breakout room with someone and we can look at that together and see what's going on.
Clara, did you put the surface, target surface equals to 0?
Please do take a minute to fill out the poll. Looks like almost everybody is finished or working on that. If you don't have any more questions for Gilberto about this session, then we can go ahead and take your break a little bit early. We'll be back at 3 o'clock for module 2.3.